Welcome to our presentation and welcome to our country, Australia. As we usually do here, we would like to begin by acknowledging the traditional owners of the land that we're speaking from today, the Whadjuk people of the Noongar Nation, and pay our respects to their elders past and present. This presentation is about activities and plans related to our support of quantum computing technology in the context of the newly formed Quantum Supercomputing Innovation Hub and future access to quantum computing services we are considering offering to the scientific community. After a short introduction, we are going to talk about why we are looking into quantum technology. Then we'll be giving some details about our collaboration with the quantum computing hardware startup and describe the scientific projects we plan to support during the evaluation and field trial phase, also talking about the challenges of hosting and integrating a quantum computer with pre-existing IT infrastructure and services. The Pawsey Supercomputing Centre is one of Australia's two Tier 1 supercomputing centres, and we are Tier 0 for radio astronomy data, since it is the place where observations are stored. We are located in Perth, Western Australia, which happens to be the most remote capital city in the world, and the POSI services are available to all Australian researchers, government organizations, as well as industry. POSI is a major part of Australia's high-performance computing infrastructure. We are supporting about 1,600 researchers, hosting 200 projects, and employing about 50 people from 17 countries. We offer supercomputing, data visualization, as well as training and consulting services. The Pawsey Centre is currently completing a $70 million capital refresh project, which, coupled with plans for ongoing expansion, will secure access to cutting-edge supercomputing technology and services to Australian researchers for years to come. The supercomputer to be deployed is composed of a mix of CPU and GPU nodes and connected to fast, low-latency storage. Next topic is why quantum? Well, reasons include growing interest. We have experienced an increase in demand for supercomputing allocations from researchers working on new quantum algorithms and simulators. Growing availability with cloud providers offering access to hosted quantum computing environments. Accelerated growth of quantum industry and research in Australia. According to a recently published report by CSIRO, quantum technology will become a multi-billion-dollar business by 2040. And we're also looking to accelerate computation with quantum computers, handling otherwise intractable problems, not dissimilar to what has been happening with accelerators like GPUs. Research on algorithms, software tools, and systems integration aspects is, of course, required. Pawsey has recently started a collaboration with Quantum Brilliance, a quantum hardware startup company, with the goal of hosting a small room temperature quantum computer at the center and integrating quantum hardware and software with pre-existing computing, storage, and networking infrastructure. The collaboration will also include a natural field trial, running applications developed by a select group of researchers from industry and academia on an actual quantum computer. This effort is part of implementing the recommendations from the Growing Australia's Quantum Technology Industry Roadmap, developed by CSIRO. Now something about the company we're partnering with. Quantum Brilliance was founded in 2019. They are an Australian quantum computing hardware vendor which builds room temperature quantum computers powered by artificial diamond. Quantum Brilliance is a spin-out from ANU, Australian National University. Some of the reasons for which we decided to start this partnership is because the offered solution seems to be more manageable than others and easy to integrate with pre-existing IT infrastructure. And the emulator environment was installed on our cloud with minimal effort. And we also like the fact that we'll be among the first to evaluate the technology, which, while being challenging, also offers the opportunity of actively participating in co-design and collaborative research tasks. Now we're going to talk about the hardware and software technology provided by the solution to be implemented. The technology provided by Quantum Brilliance includes hardware and software components. The quantum emulator enables users to develop software ready to be run on the hardware and emulate a number of qubits different from the ones actually available on the device. The emulator is already installed on our cloud, and joint work is ongoing to integrate the emulator with supercomputing resources to enable parallel computation and GPU acceleration. The quantum computer we are deploying has a form factor similar to a rack-mountable thick blade server. But my understanding is that in the future, they are looking at a size and shape similar to current GPU devices. The diagram shows the dependency of performance on size, weight, power, and cost. Larger, more expensive systems offer higher performance, but our goal is really not to outperform a supercomputer with a quantum computer. As done for the current Capital Refresh program, briefly discussed before, where we acquired exascale class technology without physically purchasing an exaflop system, we are simply interested in preparing scientists to run efficiently on future technology while minimizing operational costs. And therefore, the focus is on functionality, not performance. We are planning to offer a quantum computer and an emulating environment to help scientists augment their scientific discovery workflows through quantum computing, while at the same time learning how to address all challenges related to hosting a quantum computer and related services at a supercomputing center. The quantum computing device we are getting is a diamond quantum computer. Quantum coherence should be maintained for more than 1 millisecond. Carbon atoms in the diamond lattice are replaced with nitrogen atoms and a vacancy. A light source is used to initialize the system, and the photodetector takes care of readout operations. Microwave radiation is employed to manipulate the electron spins. The system operates at room temperature, and the connection to power network is possible through a standard PC control layer. The solution selected is aligned with current trends in supercomputing technology, where all the recently deployed pre-exascale and exascale systems include a mix of CPUs and accelerators. And software has been ported to distribute computation among devices, depending on the performance characteristics of the code. As it has been happening with accelerators and coprocessors in the past, we expect each device, including quantum processing units, to be specialized for different tasks. As an example, single core performance of GPUs is much lower than CPUs, and latency is higher. But GPUs do deliver much better performance for algorithms with minimal data dependencies, where latency is hidden by massive parallelism. And similar behavior is expected from quantum accelerators on tasks hard to treat with classical computers. We are particularly interested in exploring tight integration between classical and quantum computers, and in aspects such as triggering computation and sending data to a quantum computer from a CPU, and then merge the results back or use the CPU to post-process and store the data. As detailed in the diagram, larger and more powerful quantum computers employing different technology do require significant engineering effort to accommodate things like vacuum systems and cryogenic equipment, which makes them currently not viable for our current plans, needs, and budget.
I will now discuss a few community building activities that resulted from our collaboration with Quantum Brilliance. One of the first activities was the Quantum Seminar series, which was kicked off last year. In the first seminar of the series, titled Why Quantum, we have tried to answer a few questions crucial for those researchers that are not familiar with quantum computing. Is quantum computing for you? What is needed to get there? Why should you prepare? What are the benefits of using quantum computing? We have invited 2 researchers to give presentations about their work. Professor Jingbo Wang from University of Western Australia in Perth and Professor Lloyd Hollenberg from University of Melbourne are currently using Pawsey resources and work on designing quantum algorithms and simulating quantum circuits. Their presentations were followed by panel discussion. They even gathered more than 50 participants. The second seminar of the series was addressing quantum computing opportunities for industry and SMEs. We have invited experts in that field, Dr. Cathy Foley, currently the Chief Scientist of Australia, Andrew Housley from Quantum Brilliance, as well as industry and ventures representatives Sean Wilson and Bill Bartrey. This event was a big success and gathered more than 130 participants. Recordings of both seminars are available online on Pawsey Supercomputing Centre YouTube channel. The next step in our partnership with Quantum Brilliance is the Quantum Pioneers program, which was just launched in February 2021, based on targeted expression of interest. Groups invited to the program will be granted with exclusive access to use Quantum's Brilliance Quantum Emulator, QBQE, available on Pawsey's Nimbus Research Cloud and HPC systems. Moreover, they will also have exclusive access to the world's first deployment of a room temperature diamond quantum computer, DQDK, hosted in HPC nodes available for open science and industry. They will also participate in dedicated workshops and trainings on the use of emulator and DQDK. There will be 4 projects supported within the program, 2 research groups from Australian universities working on quantum computing algorithms and quantum computer emulations, and 2 industry partners looking at applications of quantum algorithms and workflows to specific use cases important for industry. The Quantum Pioneers program is getting into speed as we speak, with first training and workshop opportunities organized for the participants of the program and broader research and industry community. One of the biggest milestones in Pawsey's collaboration with Quantum Brilliance will be the installation of the world's first field trial of Diamond Quantum Computer, DQDK. On the way to this goal, we will work collaboratively with Quantum Brilliance to identify and manage various challenges related to deployment and integration of DQDK with HPC environment. Let me discuss a few of those challenges and approaches. We will work closely with Quantum Brilliance, their technology partners and Quantum Pioneers projects to identify and implement appropriate benchmarks. The purpose of those benchmarks will be, of course, to validate the correctness and performance, but even more importantly, test and monitor various environment conditions to make sure that those devices can operate in supercomputing data center. We will achieve this by monitoring various aspects of the environment, electromagnetic and mechanical noise, vibrations, as well as temperature drifts and fluctuations with time. We will repetitively perform a suite of benchmarks to adjust and control all environmental parameters. Among various benchmarks, we will especially focus on those addressing qubit characterization and noise spectroscopy, operation fidelity, computational error, as well as algorithm speed and accuracy. We will use the currently deployed Quantum Brilliance emulator to validate and update benchmarks if needed. Overcoming the previously mentioned technical challenges will eventually enable Quantum Pioneers projects to achieve their objectives. However, technical challenges of integration of DQDK with supercomputing data center are not the only milestones of the project. We will define the integration of the quantum system with high-performance computing network to allow hybrid classical and quantum algorithms deployment. User access, allocations, and scheduling of jobs is one another aspect which is well worked out for classical computing systems, but not yet for quantum devices like QPUs. Programming quantum devices and hybrid data workflows will be the main scope of Quantum Pioneers program. In fact, experimenting with the programming model can be already done on the Quantum Brilliance emulator deployed on Nimbus Research Cloud. We are currently working closely with Quantum Brilliance to allow such emulation at scale on Pawsey Supercomputing resources. All of this will be a learning process for Pawsey Supercomputing Centre, Quantum Brilliance, and Quantum Pioneers projects. Success of this collaboration will be based on superposition of expert knowledge in various areas of science and engineering, and will be measured in numbers of lessons learned and experience gained throughout the project. In my and Hugo's name, I would like to thank you all for attending the talk. Please keep an eye on Pawsey's and Quantum's Brilliance activities in quantum computing area. For more information, please visit Pawsey.